So thanks, Laurent, and thanks to the organizers for the invitation. It's my first time being in this place, so I'm happy to be here. I'm going to continue what Vlad was talking about. So anomalous diffusion, and I guess these are long words to spell. Spontaneous stochasticity. Okay, spontaneous stochasticity. So I want to talk a little bit about these and their connection, because they give because a lot of the intuition that Vlad and I used to build our example was from thinking about the stochastic process, and then we did the proofs with the PDE. So I want to explore how you go from one to the other. So just to remind you, I think everyone here knows this better than me. I had to ask ChatGPT last night to make sure that I was doing this right. But if you have a Markov process, xt, let's say that it's on RD. Okay. A Markov process has an infinitesimal generator. This is another word that I have trouble spelling. Infinitesimal generator is an operator L that acts on functions phi by doing this. You take phi of xt, you subtract phi at x, and I guess I should have x starting at the point little x. Let me call this x0. And then I should divide by t, and then I should have taken a limit. Okay, so this is the infinitesimal generator. And the infinitesimal generator for most stochastic processes that we're interested in right now are going to be partial differential operators, right? And so this gives you the PDE, and this is the process. And in principle, everything that you could ever want to know about the Markov process you can learn from the generator. Every Markov process has a unique generator. If you know the generator, you know the Markov process. So with some sort of abstraction, you know that all the information here is encoded in the L. All right, and that's because the Markov process doesn't have and I guess here I'm assuming that the process doesn't depend on time. So it's translation invariant in time here. So this encodes everything about this xt because xt doesn't remember the past because it's a Markov process. So it only knows its current location, and somehow by varying the phi over all test functions, you can learn about the complete law of the process xt. Okay, so example. If xt is Brownian motion, which I call w, then you know that the L is 1/2 of the Laplacian. Okay? So, for example, I can maybe make a more general statement. So let's say that I have this process, dxt equals f of xt dt. Right now, my vector field will only depend on x, but we'll add time dependence later. And maybe I put a matrix, you're supposed to call this sigma, xt, and now I should have dwt. So here's a fairly general Markov process, and then you can compute the generator by Ito's formula, and you get that the L for this is 1/2 sigma, oh actually, how should I say this? I should write a function. So this is 1/2 the trace of sigma transpose times the Hessian of the function phi plus f of f dot grad phi. And maybe I write this with a gradient like this. Okay, so that's in more generality. You can compute, let's see, so the next thing I wanted to say is that, so we have the infinitesimal generator. If you want to know about the process, you may want to know about its variance. So if xt is a Markov process, we can compute, let's say, the variance of a function of the process by doing this. Let's see, so I have to write this down. So this one is supposed to be the integral from 0 to t of L of phi of x of s ds. And I should take expectation now. Plus, and so now I'm going to use this. I'm going to use this this process, and I'm going to call this. I'm going to define a matrix A of x to be this thing. Okay. Plus this. So now I should write integral 0 to t, and I should have grad phi a grad phi at x like this. And again, the expectation. Okay, so this is again by Ito's formula. So you can compute lots of nice observables of your Markov process and their variances by looking at the generator. If
But if I may,
yeah,
because it's a school, physicists, they are more used to deal with the Fokker-Planck equation, so maybe you can make a link between the generator and Fokker-Planck equation.
yeah. So it's coming.
Do that?
Yeah. So in fact, I'm going to make the stationary Fokker-Planck. Okay. So if the L phi is 0, meaning that the phi is a solution of the elliptic equation L phi equals 0, then this term is 0. So if that happens, then that is 0. And we see now that the variance of this is somehow this sort of energy term. So this is sort of the energy density of the solution phi. Okay? So this is the link. I mean, I'm trying to make a link between the energy of the solution of the PDE and the variance of the process, so that I can make a link between, because anomalous diffusion is going to be a statement about this, and spontaneous stochasticity is going to be a statement about this somehow. Okay? So I'm trying to make the link as fast as I can. If you ask me for the details, I'll blunder them up because I don't know them very well. I can't remember Ito's formula. So the proof of all these is Ito's formula, and then if you ask me to prove it, I'll miswrite Ito's formula. But the proofs are in principle one line. Okay? So in particular, if we want to study the process, we can find hopefully, one strategy would be a large family of solutions, phi of the equation L phi equals 0, and then we can learn about these variances. We can learn about the variances of phi of the xt from the energy. The energy density, grad phi, a grad phi. I think maybe there's a 2 somewhere. I think that there's supposed to actually be a 2. Well, no, I think that's okay. Yeah. Okay. All right, so this is the link. So notice that I did not say, so you could think, oh, I let phi be just one of the coordinate directions, or I let phi be the identity, basically. And I can learn about the variance of the process itself from this. But I didn't say that that sort of affine functions are going to be solutions of my equation. So that doesn't necessarily work. So I said that the xt was Markov, but I didn't say that there's no drift right? The F drift term can mess up the fact that the phi is a solution if it's affine. So if phi of x equals, I don't know, one of the coordinate directions is a solution, then we can learn about xt itself, or at least its variance by looking at phi of xt, right? But this won't be the case in our example, okay? All right, so anyway, this is the connection. This thing here, if phi is a solution, then this thing is called the quadratic variation of xt. Okay, so a Markov process can have a quadratic variation, and that's sort of a measure of the local, how strong the diffusion is sort of locally at that point. So, so the energy density is exactly just giving you the quadratic variation of the process, and that's the connection between the sort of energy of the L2 energy of the solution and these processes. So, let's go back to our case, back to anomalous diffusion, and try to understand what's going on. So we had a process like this, or actually no, we had a PDE like this, theta kappa, and we had a vector field, which, what letter did you use? F? Okay. F. I didn't write any time dependence in my discussion there, just to keep it simple. But you can put time dependence everywhere, and it doesn't change anything. If you put time dependence everywhere, then you would want this guy to be a solution of what you call the Fokker-Planck equation, what I would call the backwards Kolmogorov equation. And that equation is the equation like this. Okay, so it's the backward in time Kolmogorov equation. Okay, so back to anomalous diffusion. So we have this equation. This thing is, so if you think of this whole thing here as L, this is the L for xt, where now we see if I can write it. Should be easy. So dxt equals f of t xt dt plus square root of 2 kappa dwt. Okay? So here's the Markov process. This is what Greg was writing, and this is the PDE, which is what Vlad was writing. Okay. Okay. So the statement of anomalous diffusion means roughly that for all initial data, in some suitable class, but whatever, let's just say for all initial data with 0 mean on the torus. Okay, if we solve the equation, the parabolic equation, write it again. Okay, so this is at time t equals 0, and this is in all of time across the torus, Td. Then the limit, or the lim sup or something, of this guy stays bounded away from 0. Okay, as kappa goes to 0. Okay, and so this you should think should be related to, I mean, it's saying that the quadratic variation, at least when you average over, starting points given by this, should stay bounded away from 0, should be positive. And so that should be the same as saying that the variance of this is positive. So let's see, spontaneous stochasticity. Huh? Yeah, I forgot to write. Yeah, I should have just written the norm here. Thank you. Okay, so I don't have room to write this on the board. I still have a blackboard behind here somewhere, right? I can go up. Yeah.
Also, because this is a school, it would be very important that you comment and repeat that the study of the flow of a given vector field is related to the passive scalar equation in a very crucial way. And that's very important information for many people here. I'm not sure it's completely.
What do you mean?
So like studying the flow, the advection of a particle by a given vector field F is by the method of characteristics. It's directly related to study the advection of a passive scalar with given diffusivity. That's a very important information. I'm not sure it's completely.
Okay, so maybe that's what I'm trying to explain. Yeah. Because these are the trajectories,
yes,
and this is the equation. Yeah.
The formula related, like theta kappa is equal to
expectation. Yeah, okay. Yeah, so you could write, if you want, theta kappa of t and x. Okay, so now what's the formula? It's going to be expectation. So it's going to be integral 0 to t. How do I write this? Yeah. So I'm supposed to write the initial data. No, I don't write that. I don't write this. Yeah. So I write x of t. Yeah. There's no right-hand side, so I just write this, and now this is supposed to be the backwards guy, right? Yeah. Okay. So I would prefer to write this equation backwards.
It's just the initial data. You evaluated at x of t and then expectation.
Yeah. I don't know why I write t. Yeah. Okay. So this is not quite right because I have the equation written backwards, right? Yeah. So I think I need to change. Okay. So this is an antisymmetric term, so I should change the sign there or something.
This is the solution of the negative.
Yeah. This is the kind of I can't remember this kind of detail. Yeah. So I should say that this is the case where now I think I have to change the sign here. No. I set it up correctly because these are different. Yeah. Okay. Okay. So this is not quite the L because it's the L for the minus F, I guess. Actually. All right. So there's some backwards thing that always happens that I can't keep track of. Okay. So yes. So if you want to compute what this solution is, you can write it in terms of the trajectories like that. Exactly like that. Okay. So given that this thing should be connected to the variance of the process, so I think that the correct way to say at least part of spontaneous stochasticity refers to something like a statement like x. So now I should index the x by some kappa, I guess. I should call this kappa. That this is going to converge. So I guess what I should say is that the law, the probability measure of this thing converges weakly. As kappa goes down to 0 to a non-degenerate stochastic process. Okay, and most of the work there is in the word non-degenerate. What that means, right? So I think if you scale Brownian motion, it will converge to a stochastic process, but it'll be 0. So non-degenerate means that somehow the variance of this limiting process, let's call it x bar of t. Non-degenerate just means that the variance of this is strictly positive. Okay, so it's not 0. Okay? And so you can see that there should be a connection between this and stuff like this because of this Ito stuff.
This last requirement holds for all t positive?
Yes, yes. So I think if you want it to be, I mean, I suppose it could be degenerate for a while and then become non-degenerate, but yes. So this should be for all t. I guess in this case, I mean, if you want to link it to this statement, maybe you just want it at time 1 or something. But okay, so that's the link. I mean, in general, there should be a way whenever you have a statement about the sort of Fokker-Planck equation here, the PDE, there should be a way to translate it into the stochastic process. I mean, it's sort of obvious because there's a simple formula, but you know, if you're a probabilist, you will speak about the process, and if you're an analyst, you may speak about that PDE, but you're often speaking about the same thing. Okay, so in my view, this spontaneous stochasticity, if not identically the same definition, is very closely related to anomalous diffusion in that sense. Okay, in fact, the probabilist would call anomalous diffusion a statement like that maybe this doesn't converge weakly, but that this thing's variance is bounded below or scales differently in t. I mean, as kappa goes to 0. Okay. Okay. So now I want to try to convey some intuition for how we can make a vector field that has a property like that. Okay. So if there is a diffusion anomaly for some f, it has to be that the second order term in some sense does all the work. The diffusion, you know, let's just call it the Laplacian, must do the work. Okay, and it's because this term, I mean, how do you get this term derived? You differentiate you multiply by theta kappa and you integrate by parts, and this term completely drops out. And so this term just comes from this Laplacian term, and so the first order term has nothing to do with the creation of that term in some sense. Of course, the vector field can enter because the solution itself depends on it. Okay, so however, and these are all kind of obvious things, but the solution theta kappa depends on the f. Depends on f in a very complicated way, in a possibly very complicated way. Okay, so now let's look at this diffusion term for a second. It's actually easier to prove the result when the theta initial is very, very smooth. So a Fourier mode with low wave number, low frequency Fourier mode, for example. If you make there be a lot of oscillations, the proof becomes harder, even though usually for an equation like this, if you would just have the Laplacian, it would decay faster if you had a higher Fourier mode. In our case, it's more difficult. So how are we going to get a sort of low wave number thing here to have this term do something to it? Because just imagine kappa is very, very small. Then that Laplacian term really only acts on very small scales. Okay, so the kappa Laplacian term acts on scales. Okay, it kind of depends on the f actually, but let's just say the f is sort of of order 1. So this acts on scales of order square root of kappa, right? So those length scales are very, very small. And So this is a very, very small number. So if your initial data had wiggles, which were varying on a scale much smaller than square root of kappa, the Laplacian term would kill them, right? It would just smooth them out, and they would be erased, and they would essentially average. But things that are living on much larger scales than the square root of kappa, the Laplacian term doesn't really do anything at all, okay? So the only way that we can make the anomalous diffusion happen is if somehow the vector field, without any help from the Laplacian, takes the smooth initial data and creates a bunch of small scales somehow in time 1, because we only have one unit amount of time, but it's just going to create a bunch of small scales. So, and then finally the scales will be so small that it's created that the Laplacian can erase some. And then by sort of erasing these wiggles, you see the energy term will pick up something, okay? So it's going to have to look like this. So let's say that this is just a cartoon. This is the initial data. And now I'm going to write, actually I should have written time going up, right? So let me erase this. So I'm going to try to draw a cartoon now of how the thing is supposed to work. This is very impressionistic. Okay, so you have some initial condition, and so time is going like this. And we hope that after some time, the initial condition starts to pick up some wiggles like that. And as time goes along, these wiggles start to get really, really fast. Okay? Until the point where the gap between them is less than square root of kappa, and then they get kind of averaged. So then they kind of look like this. And you see that this has more, what did Greg call it? Intensity than that. Okay, so the intensity gets erased by the Laplacian. At the level of the particle, the particles, I guess, I mean, what you would, if you're thinking about, dropping ink into a roaring fluid, at first the blob of ink is very smooth, then it starts to kind of, make weird, crazy shapes that, the boundary of the blob gets very, very messed up until finally it gets so, the length scales that are created are so small that the friction term just erases them, and they kind of, it becomes all one color. Okay, so we have to make a vector field that does that. Okay, so in order to do that, we have to cross, you see, a lot of scales, because this thing varies maybe on scale 1, because it's a very low wave number, and now this has got to vary on scale much, much less than square root of kappa, and so there's log kappa mini length scales in between. Okay, so we have to to create wiggles across log kappa mini length scales. Okay, so that's what we have to do. Is that clear? Is this pedagogic? Yeah.
Enough.
Okay. Yeah. If it's not pedagogic enough, you tell me. Okay.
So
Yeah.
I have a question also. So usually when people are making the passive scalar advection, they use a forcing. They force the equation to make it stationary. So how the picture is changed when you are keeping injecting scalar into the problem?
So if you put an F over there, like
Yes.
on the right-hand side, I guess not F, but G, you put
Yes.
some right-hand side.
Yes.
Yeah, so if G was smooth, I mean,
Yes.
what does that mean? Now I have to write my time integral thing. Yeah. I mean, do you want me to write it? Yeah, so you can put a right-hand side there, and you can write it in terms of the process again. Yeah, that's what I was trying to write before. Okay. All right. So I want to talk about now how we're going to make an example that does this. Of course, because when you see something like this, we have to create it across many scales. There has to be infinitely many scales because kappa is going to go to 0. So this is essentially just infinitely many scales, and so there has to be some sort of fractal thing going on. So there's some kind of fractal nonsense is necessary. Some kind of fractal construction is needed. Okay? So we're going to try to create wiggles kind of one scale at a time. And what we want to happen in our problem is that the creation of these wiggles somehow somehow enhances the diffusivity. So if you think about the process, this is going to have a lot of wiggles, and somehow that's going to increase the variance of this, even though it looks like the variance of this is only coming from that. So you can think about the same thing I just said about the process. I said this is only caused by the Laplacian term. Well, the variance looks like it's only caused by that, because if you look at the variance again, it's all the way up there. It's again that sort of quadratic term with the A. The A only involves the sigma. The sigma is only multiplying the white noise. It doesn't involve the F at all. So how are we going to increase the variance by just this F? So I want to give one baby example, just to build intuition for how you can increase the variance by using a vector field. Okay. So here's all right. So toy example. I'm going to give two toy examples, and then it turns out that the second toy example is going to be what we use to actually build our vector field. Our vector field is going to be some fractal construction out of the toy example. Okay, but the first toy example is actually harder to analyze, but it's actually easier to think about, so I'm going to do it first. Okay, so I'm going to talk about a cellular flow in 2D. Okay, so I'm just going to draw a picture of what the vector field is supposed to look like. I'll make this picture big, and then I'll zoom out on the picture in just a second. Okay, so I'm going to make a periodic F, which only depends on x. There's no t dependence. And the F is going to turn in circles in each one of these squares. Not exactly circles. Towards the center, it's going to be a circle like this. And then as you get sort of further out, it becomes more squarish, like this. Okay, so you see the direction. This one is, what direction is that? Counterclockwise, right? And then in the next cell over here, it's going to be just the reflection of that. So it's going to be the clockwise version. Okay, and you see that the arrows line up across the interface, so they're both kind of going in the same direction. So there's no discontinuity. This vector field is smooth. In fact, you can write a formula for the vector field down. I think that what you want to do is you want to write the formula for these streamlines. So you write psi of x1, x2 is sine 2 pi x1 times sine 2 pi x2. Didn't use the board very well there. Okay. Okay, so this function is going to have these things as its level sets, and then you let the vector field, let's call it f of x equals grad perp of the psi. Okay. And you'll get this. Okay, so I'm going to draw this one. It goes clockwise again, and then this one down here should go counterclockwise. Okay, now let's imagine that we have, and so this vector field, the strength of it is of order 1. The size of these cells are of order 1. Okay, so everything is of order 1 here, and the vector field is totally smooth. How can this vector field enhance the diffusion or enhance the variance of the process? So try to imagine what's now going to happen if you run a simulation. So I have simulations on my computer. I can show them to you if you're interested. What happens is if you let's say we start a particle at the center of this square, and actually let me zoom out a little bit on the picture. I'm going to draw another picture just with more squares. Okay. Okay, so here's a sort of zoomed out picture. If we start with a particle in the center, it'll kind of wiggle a little bit because of the Brownian motion. And again, the kappa now we're supposed to think of it as very, very small, like 10 to the minus 8. You know, and this is all 1. So basically, it's going to follow the streamlines, right? It's going to follow the ODE trajectories around. And you may think, oh, I should just think about this process as a perturbation of the ODE flow. No. Because it's not that at all. Because what's going to happen, it's going to go around and around and around. But as soon as it gets close to the boundary of two squares, within the square root of kappa, it can switch sides randomly because the diffusion can kind of kick it across one side versus the other. So once it gets close to the edge, the diffusion can just like have some kind of hiccup and push it there. And now it's going the other way, but it's still kind of in a boundary layer, so maybe it can do this many times actually. And what happens, what you see for small kappa is that the thing goes in a circle for a while, and then once it gets in a boundary layer, it starts making a pattern like this where it basically does a random walk on the lattice until it gets stuck again. Then it'll get stuck for a long time, and then it gets in a boundary layer and does another random walk. Okay, so the square root of kappa, the square root of 2 kappa term destabilizes the nice, smooth ODE orbits. In some horribly chaotic way. Okay? The original chaos that the Brownian motion has is very small. There's just kappa. But the chaos that's created because it's destabilizing the orbits is much, much greater. Okay? So now if you zoom out on this picture, what will you see if you zoom out really, really far so that you see like 50,000 squares and you wait a long time? What you'll see is a random walk zoomed out. And that random walk will look like another Brownian motion. And you can see very well that this doesn't have any preferred direction, so it has to be another multiple of a Brownian motion. So if we zoom out, this process looks like another Brownian motion. Okay? But the trajectories of this Brownian motion really have nothing whatsoever to do with the trajectories of the original Brownian motion. Not quite, I mean, they depend on it, but in some way that you'll never be able to extract, okay? Because the little, it's like it's really like the butterfly effect, right? The butterfly flapping its wings can cause a hurricane. The hurricane did depend on the butterfly flapping, but you'll never be able to unravel that information. So a little bit of chaos from the butterfly can create a big chaos, okay? So it's kind of like that. Now the question is, what is the variance or the size of this new Brownian motion? What is the new diffusivity? With diffusivity, and I'm just going to try to compute the order of the diffusivity. Trying to compute the exact diffusivity that it has is going to be hard. But let's imagine kappa is very small. Okay, so what happens is when you're in the center of this, when you're in the center of a square, you do nothing. And only when you're in kind of a boundary layer do you actually start to do a random walk. And so the boundary layer where things are sort of active is of size square root kappa. Okay? Because that's the thickness that you need so that a Brownian motion can put you through that distance in time 1. Okay? And once you are in this layer, you basically do a random walk with speed 1. The time between the steps is of order 1, and the size of each step is of order 1, so you do a regular Brownian motion when you're in that layer. And when you're not in the layer, you do nothing. Okay? So what should the variance be? Well, the variance of what should the diffusivity be? The diffusivity of a random walk like that is of order 1, and the proportion of time you spent doing that is square root of kappa, because the particles here, because this is a divergence-free field, the particles are not going to concentrate anywhere. So you just, the particle, after a long time, by the ergodic theorem, will spend as much time in any part of the torus as any other place. So the proportion of time it spends in that layer is square root of kappa. So the limiting diffusivity is actually square root of kappa, up to a constant. Okay, and you can actually, if you're very careful, do some careful analysis of this and figure out that there's an exact constant in front of the square root of kappa and compute the next order term and stuff like that. And a bunch of people did this in the 1980s. People were interested in that. Okay, so the square root of kappa, you'll notice, is much, much bigger than kappa. So really a huge increase in the amount of diffusivity was caused by this really peaceful, nice, laminar flow. Okay, and so now, but square root of kappa is not of order 1. We need it to be of order 1 to get anomalous diffusion. So that's not of order 1. Okay, so this example will not give you anomalous diffusion. As kappa goes to 0, this thing will still go to 0 because the variance of a process with diffusivity square root of kappa goes to 0 as kappa goes to 0. Okay? But what you could imagine doing, and the idea that Vlad and I had, which turns out to be, we're not the first ones to have this idea, is that what if you kind of glued this picture together across many, many scales? Okay? So you start with a little Brownian motion, and you destabilize a vector field at some scale. You zoom out on that picture, and now you see a new Brownian motion. And that Brownian motion maybe destabilizes the orbits of the vector field at that scale. Zooming out again, you see a new Brownian motion again with an increased variance again, or increased diffusivity again, and you cascade that across infinitely many scales. Okay? So the diffusion that you see at any scale, if you really zoomed in and looked at that diffusion, you wouldn't find just a dW term. You would see the vector field. And you keep zooming, it's like you keep seeing the vector field all the way down, but it looks at any scale like a diffusion. Okay? And notice that you cannot follow, like you can't figure out what this trajectory is going to be by following carefully the orbits of the ODE and treating the kappa term like a perturbation. Okay, that won't work, because if you do that, the orbits of the ODE just stay bounded. Okay, so this like crazy Brownian motion that happens cannot be understood by some sort of analysis of how the vector field is mixing or whatever. It's just not going to tell you that. Okay. Sorry?
Even if you follow only with the boundaries, the trajectories of the boundaries?
I mean, somehow it is going to be a function of that Brownian motion, but it's going to depend on the Brownian motion that you see on this larger scale will be a very kind of singular function of the little tiny variations. Like, I mean, if you take the Brownian motion, you break up the Brownian motion into its frequencies. The new Brownian motion that you get will be a function only of the very, very high frequencies of that Brownian motion. And so it's not going to be, you can't compare it to, and when you do this across many scales, it's like that information is lost. It's like entropy has happened. You're not going to be able to follow the trajectories anymore. Okay?
Can you repeat the argument underlying the square root for the diffusivity
Yes.
based on the boundary layer?
So basically, when you follow this particle, it essentially has two states. When it's in the boundary layer, and when it's not. And when it's in the boundary layer, its diffusivity is of order 1. Because it's doing this random walk at speed 1. So that's going to give you diffusivity of order 1. Yeah. Diffusivity is length squared over time, and both the time scale of the switching and the length scale of the jumps are of order 1. So it's going to be 1 divided by 1 is 1. Okay, so the diffusivity is of order 1, and it's going to experience diffusivity of order 1 only when it's in the boundary layer, and the proportion of time it's in the boundary layer is the same as the proportion of the boundary layer in space. Because the particle is going to, Lebesgue measure is the invariant measure for this process. So there's no preferred place where the particle is going to hang out. It's going to hang out sort of everywhere on the torus equally. So the amount of time it spends in the boundary layer is square root of kappa. The amount of time it spends everywhere else is 1 minus square root of kappa. And when it's in the center of the square, we just say nothing's happening, because essentially nothing is happening. So it's going to be square root of kappa times 1 is the sort of overall diffusivity that you experience if you average over a long time. Do you buy it? So you can make this completely rigorous. Yeah. Okay. All right. So anyway, so our idea is to build a cascading an example. Before I move on from this example, let me talk about the PDE version of this. Because so this is the process. I said that this should happen. And how can we see that by looking at solutions of the PDE? Okay, so now I need an eraser. Where did I put the eraser? So here's one. All right, I guess I should start trying to bring these boards. No, I still have boards here. Okay. All right. So, No, this is just an example of what they call enhanced diffusion, right? Because the diffusion has increased from kappa to square root of kappa. So it's been enhanced. What anomalous diffusion is it's enhanced diffusion iterated over infinitely many scales. So that what happens is that at very small scales, the diffusivity is kappa. Because if you're looking at such a small scale that you don't see this random walk, then you just see the kappa. Okay, so at small scales, the diffusivity is kappa. If you zoom out past this checkerboard and go until you can see 5,000 squares, then it looks like the diffusivity is square root of kappa. Okay? So we could think about the diffusivity as kind of being a function of the scale that you're looking at.
So the square root of k with fixed point, or if I continue zooming out, like something like a renormalization to like get another?
Yeah, so for this problem, there's only two scales, the small scale and the scale of the checkerboard. And so you won't continue to enhance as you zoom out if you only see that. But it could be, maybe, that as you continue to zoom out, you encounter more vector fields that do stuff like that at every scale. And then it could be that as you zoom out, you continue to increase the kappa. And you should think about the kappa as a function of the length scale, right? And so that would be anomalous diffusion if the kappa diverges with the length scale in some sense, yeah. Or as much is going to 1 as the I mean, depends on how you think of the length scale. If you think of the small scale of order 1, then as you zoom out, then the kappa should go to infinity. If you think about this kind of scaling where the big scale is of order 1 and the kappa goes to 0, then you want that no matter how small kappa starts, as you zoom out from that small scale, the kappa goes to 1. The renormalized kappa goes to 1. Yeah. Okay, so this is what I'm trying to explain now. Okay, so I want to explain how you would see this, though, in terms of the PDE. Okay. So, all right, in terms of the PDE, okay, given what I've written on all these other blackboards, it is natural to look for, to consider the solution. So I'm going to rewrite this. So what is my equation here? Let me take this thing and I'm going to rewrite the equation just here. So the L is going to be kappa Laplacian plus or minus, I guess, plus or minus this F dot grad. And I'm going to do a trick, which is to write the L in divergence form like this. Divergence of kappa times the identity matrix in dimension 2 plus the matrix which is 0 minus psi 0. And okay, so I didn't use let me rewrite it. So I'm going to write it as divergence kappa identity plus 0 minus psi 0 grad. Okay? So you can write the incompressible vector field F as a skew symmetric term in the diffusion matrix. Okay? The reason is that when this divergence hits the matrix, it creates the F. And when the divergence hits the grad, it makes a Hessian, which is a symmetric tensor. And when a symmetric tensor contracts against a skew symmetric tensor, it gives 0. Okay? So you can write this F into divergence form like that. Okay? And so this is helpful to think about. I'm going to call this for right now A of x. Okay? So A of x is just, I could have written it like this right away. Okay, so the incompressible drift vector field that we have, this thing, is encoded in the antisymmetric part of the diffusion matrix. Okay, that's actually what the antisymmetric part of the diffusion matrix is. It's just encoding an incompressible vector field. All right, so anyway, in terms of the PDE, it's natural to consider solutions of L phi equals 0. That is, let's write what that means now. It means minus divergence A of x grad phi equals 0. Okay, so we have this nice now divergence form PDE. Now, what I would like to do is, because I really want to get information about the process x itself, and I have a phi up there, so I can compute the variance of phi of x of t. If phi is a solution, the first term drops out, and I just get that energy. I'm going to try to find a phi which is almost a coordinate direction, right? It's like I said, if this was xj, then we can learn about xt itself. Well, that's not a solution, xj, because if you plug in xj in here, you see that it creates some stuff. I mean, it's not going to give you 0, okay? Because that phi of x is not a constant. So so we will try to find solutions. Sorry, I'm struggling here. I have a little bit of a cough. We're going to try to find solutions which are close to that sort of just xj coordinate direction, but are not quite that, so in order to make it a solution. So we're going to try to correct the affine xj so that it's a solution. I'll call it phi ej, such that, so I'm going to look for something that is close to being just ej.x, so that's just xj, plus some periodic function here. And this thing is called the periodic corrector. Okay, the reason that I can ask that it be periodic in this case, so it's periodic and mean 0. So I also want that this is mean 0 on the torus. Okay?
Sorry, can I ask?
Yeah.
That equation diff A grad phi equals 0. So physically that means you're looking for a steady state of a cellular flow plus diffusion. Isn't that just the uniform solution? Is there any other solution?
No, phi equals 1 is a solution. Like constants are solutions, which we were kind of using earlier. But we now want to find not the constant solutions, but the kind of affine-like solutions. Okay? The affine-like solutions can tell us about the variance.
I know what you're trying to do. I'm surprised that physically that if you have a cellular flow and you add diffusion to it and you wait into time, it seems strange that you can get any solution that isn't just constant. But yeah, you're sure.
Yeah. I mean, you can compute it. It's actually computing. You can compute it in one line. So, all right. So this equation, divergence A of x grad phi, has periodic coefficients. So you should look for kind of periodic solutions. If I rewrite the equation in terms of this periodic function that I seek, the equation just looks like this. And this equation, if you know about the theory of homogenization, is just the corrector equation. Okay, so this is the corrector equation. Okay. Now, let's suppose for a second, so I can write down an exact, I can write down this solution in, no, I can't for this thing write it in exact form, in closed form. But I can, so in order to prove this thing, what you can do is, instead of like following around these trajectories and making probabilistic arguments, you can actually just compute this solution, and that will tell you the diffusivity as you zoom out. Why? Well, let's suppose that I can solve this thing. Okay? So then we compute the variance of, let's say, xj. So our process xt.ej. Okay, that's equal to the variance of phi of ej of xt plus the variance of the difference. So I guess this is just I should subtract them, right? Okay, so let me do it like this. Minus 5. Okay, so I'll write it chi of ej like this. Okay, So I plugged in this formula. I just confused you by like erasing it 5 times, but I just plugged in that formula. Now this one, because this is a periodic function, it's bounded. So this is of order 1 as t goes to infinity. Okay, it's going to be of order 1. So I can sort of drop it from the variance. And so I can say that this is going to be like the variance of this thing plus an error of order 1, essentially. I think that's not quite how quadratic things work, but that's essentially what you do. And now this one is a solution. So I can plug it into my formula up there, and I get that this one is equal to, so I'm just going to, now I'm going to drop this. Because as t gets large, this should scale like square root of t, so it's going to be much bigger than the other term. I look at this term, and I get expectation of 0 to t of grad phi ej xt dot a xt grad phi ej xt. So I get the energy density, right? Okay. Now we know that the process here, the Lebesgue measure is the invariant measure for the process. So if you start at a random point in a torus and you look at, where the process goes, it'll spend the same amount of time everywhere. The Lebesgue measure is invariant. So by the ergodic theorem, this thing, if I divide by t, has to converge to this, equals, so in the limit as t goes to infinity, this is going to be t, because I have this integral, times this integral in space. So td, or t2 in this case, grad phi ej of x dot a of x grad phi ej of x. Okay? Let me say that. So it's t times that. And so this thing here, the variance of the process in the jth coordinate direction is going to scales like t times something, and so that something is the diffusivity. So this is the diffusivity. Okay. Now I have to erase something, so let me do it down here. Okay. Okay. So this says that the limiting diffusivity on large scales should be this number, grad phi ej dot a grad phi ej. And in our case, because this is now symmetric, the skew part drops out as usual, and so this is just kappa grad phi ej squared. Okay, so this is the energy density of the corrector, or this is the energy, I guess, because it's being integrated, of the corrector, or of the corrected affine. Okay, and this is also the formula in terms of in PDE theory, this is how you build the homogenized equation. Okay, so this is the let me see this. So in terms of PDE, we can show that solutions of the equation, so let's say, I won't write the time-dependent equation for now, plus f equals 0, converge to, or rescale, converge in a rescaled limit. I'll just say converge on large scales to the to solutions of this equation, minus divergence A bar grad theta bar equals 0. I should go over here. Stop it. And this matrix A bar is given in general as in the following way. So A bar is a matrix, deterministic and constant, given by kind of polarizing this formula. So you would have just A bar ij equals integral kappa grad phi ei dot grad phi ej. Or if you had if you write it in the general form here, then you would just have, in terms of the A, you would write it like this: grad phi ei dot A grad phi ej. Like that. Okay? So what you can show by looking at just this, by basically finding this corrector, and which you can solve very easily, and then computing it, you can compute the limiting A bar, and you can show the PDE converges to a limiting PDE, and that will tell you that the limiting, that as you zoom out on the stochastic process, it converges to a Brownian motion. Because this equation here is just a Brownian, is the equation of a Brownian motion, because the A bar is a constant. And it's a constant matrix, so even if it's has different eigenvalues, it's still going to be a Brownian motion just kind of stretched in some direction. Okay? Is that clear?
How come that is consistent with the square root of kappa?
Yeah, so what you'll show is if you compute these guys, which you have to compute it very carefully, what you'll show is that this number is of order square root of kappa, and then you can times a special constant, which you can compute, and then you can compute that the next order error is the kappa to the 1/4, I think. Blah, blah, blah. Okay? So you can't write down a formula for the corrector, but you can compute this. I'll tell you what the correctors look like. They look a little bit like the process says they should. What the correctors should look like is, it's kind of hard to draw them, but what you do is you basically take an affine function, and in a boundary layer of the cubes, you let these functions phi be the affine function. But on the interior of the square, you kind of make them be constant. So if I took a cross-section of this, it's hard for me to draw a 3D surface over a 2D grid like that. But what you would see is, if this is the affine, then the corrector is going to look like, and these are the boundaries of the cubes, the corrector will look like this. It'll look like this, and then go up, and then be constant, and then go up, and then be constant, and then go up, kind of like that. Okay? And the thickness of this, like, I'm not drawing it very well. It's supposed to have all of its gradient in this boundary layer. Okay? And it's supposed to make jumps of size 1 in the boundary layer of thickness squared of kappa. And when you compute what that does here, you realize it gives you square root of kappa. Okay? So it's like, and the corrector is reflecting the fact that nothing much is happening on the center of the square, and all the action is happening kind of on the boundaries. And so the corrector is going to have that kind of shape. There's no formula, but you can make an expansion in kappa of that. And a bunch of people studying this did that in the 80s. Like Papanicolaou has a whole paper doing expansions in kappa of that.
So your
Okay.
corrector gets what when kappa goes to 0?
When kappa goes to 0, the corrector just has all its energy in the little boundary layer and makes big jumps. Yeah. Okay. And we'll see that for in general for these fluids, right? Like if you have a very rough vector field and you have many scales, the solutions of the PDE will have all of their sort of energy in very small sets, like a Gaussian multiplicative chaos or whatever, like a multifractal does. And this is sort of one scale, but okay. All right, so I better at some point try to explain now what the vector field we make actually is. Or I'm going to leave all of the sort of hard work to Vlad. Okay, so I have to tell you a second example. In this example, we can write down the corrector explicitly. We can compute the enhancement of the diffusion. And then we can talk about trying to stitch together an example that does. The second example is kind of, that makes a fractal out of the second example. Okay, so toy example 2. Now it's going to be a shear. Okay, so now the psi of x1, x2 is going to be, I have to get all the constants right or everything's going to be a mess now. So just a second. So this is going to be I'm going to have a parameter a, which I'm going to allow myself to vary. Epsilon is going to be a length scale. x2 over epsilon. Okay, so this is a function. And now I'm going to look at grad perp of this, and this is going to be my vector field. Okay? So this is going to be a shear. So this is going to be, I'm going to leave a and, it's supposed to be epsilon. A and epsilon are going to be parameters I'm going to follow around. Okay. So what does this look like? This is going to be a shear in the x1 direction, right? So this is going to be 2 pi a epsilon cosine 2 pi x2 over epsilon times the E1 direction. Okay, so what does it look like? It's just a very simple shear. You've got channels. The channels have width epsilon, or maybe epsilon over 2 or something, but it's going to go roughly this direction in one channel, then it's going to switch to that direction. Okay? Then it's going to switch to this direction. Okay? And the strength of the vector field is sinusoidal, right? So it's going to be here, it's going to be continuously varying. In the center, it'll be the strongest. It continuously varies so that it's 0 here, and then it goes back the other way there. Okay? Now, the strength of the vector field is of order a times epsilon. So the length of these velocity vectors are of order a times epsilon. Okay? So this is our vector field. Very simple. Now, we originally, when we were trying to write our paper, we were trying to use this example. But this example doesn't work for what we want. We can't, if you make a fractal out of this, you won't do as well as if you make a fractal out of this. And the reason is that the space in the domain where the dissipation is happening here is in a very small set, whereas here it's going to be kind of in a set of full measure. It's going to be like we're using the full space that we have to make the diffusion anomaly. So the enhancement here is going to be much greater. So I want to compute really quickly what this vector field does at large scales. So by the same kind of picture as we had here it's actually easier to analyze. What's going to happen? Well, the vector field, because of the vertical diffusion, is going to randomly kind of move up and down. But it's going to basically move, let's say the arrow's going this way here. The Brownian motion is going to go this way at basically a constant speed. But the vertical diffusion will eventually kick it outside of that channel, just sort of randomly, and it goes here. And then it'll start going the other way until finally it goes in a different channel and it goes this way. And you see it can go back and forth. And the amount of time it spends in the channel is going to be kind of random. It depends on the vertical diffusion, which is unaffected by the vector field entirely. Okay? So what ends up happening is it takes, if it takes delta t time, this is the time to switch channels. So this is kind of the characteristic time scale. How long does it take to switch channels? Well, it's got to overcome a distance of epsilon. It's got to move a distance of epsilon in time t, or time delta t, with diffusivity kappa. So kappa is going to be epsilon squared over delta t, right? So that means that this is going to have to be, because it's length squared over time, that's the only way that you can make the units work out. And so then you get, this is epsilon squared over kappa. Okay? So the amount of time it takes for you to switch from one channel to the other for your diffusion is of that order. I'm just doing a calculation trying to get things of the right order at this point. Okay? So that means that how big are the steps then? So how big is delta x, which is the typical step size? That is going to be, well, delta t times the strength of the velocity, I guess. And the strength of the velocity is this. So it's going to be a epsilon times this, so a epsilon cubed over kappa. Okay? That's a typical step size. So in the horizontal direction, we're doing again a kind of random walk where we take steps of size this, and the time between steps is that. Okay? So did I compute this right? Yeah. Okay. So I think that's correct. Sorry. Okay, so the new diffusivity then, so the effective diffusivity of this random walk on large scales needs to be I guess in the vertical direction, it's just doing the same diffusivity as before. It's unaffected by the vector field. But in this direction, you see this random walk. And when you do the length squared divided by time, again, you get, make sure I do this correctly. So I should get a squared epsilon 6 over kappa squared. So I'm trying to make delta x squared over delta t. And so I get, this is delta x squared, and then divided by delta t is kappa divided by epsilon squared. And so we make a squared epsilon to the 4th over kappa. Okay, another way to say that is it's kappa. So this is in the horizontal direction. It's kappa times a parameter, a squared epsilon to the 4th over kappa squared. Okay, so this is in the horizontal direction, in the E1 direction. And it is just equal to kappa in the E2 direction. Okay, is that clear? I'm just computing the diffusivity of this random walk using the same reasoning as before. So I get this number. If you do the calculation with the correctors, it turns out that in this case you can compute the corrector exactly, and you can compute the diffusion matrix exactly from that. So let me do that really fast and just write down the answer. Because this vector field is really 1D, and because it's so 1D, I can just write down all the answers. And I think that this answer was, this sort of homogenization problem, as it were, was done before homogenization existed by like 50 years, and it was done by people working in fluids, and they call this thing Taylor dispersion. I'm supposed to call it Taylor. Do you know about that? Taylor dispersion? Okay. It's called Taylor diffusion. Well, the referee told us we had to call it Taylor dispersion. Okay. Anyway, so the corrector in this case you can compute. If you write it as a function on the torus, then you get. I'm just going to write down the answer, and you can plug it into the equation and check it if you're interested. It takes about one line. 2 pi y2. So that's the first corrector. The second corrector is 0. And so when you compute the homogenized matrix like I did up there, what you get is that the A bar, the sort of large scale effect of this thing, is kappa plus 1/2. So I'm getting the exact constants now. The only difference between what I wrote there and what I'm writing here. And you see that we have a lot of stuff happening in the E1 direction, but nothing in the E2 direction. So we've enhanced in the E1 direction, but not the E2 direction. Okay? So this is what you get. So it agrees with my kind of back of the envelope calculation, but here we have the exact constant with no error, nothing. Okay? Because we can compute it. All right. So what's important for us when we build this vector field, which I think I'm going to have to let Vlad explain this afternoon, is, right, because we're trying to do this in a way where we see, we're going to take these shear flows, we're going to do horizontal shears and vertical shears, and horizontal shears and vertical shears in a kind of alternating pattern. And we alternate them so that the horizontal guy gets some enhancement for a while, and then the vertical guy gets some enhancement for a while, and they trade back and forth, so they're both going to be enhanced the same amount, and we don't have some weird anisotropy happening. Okay, so we just do that. We alternate them. Well, we can't do both at once, except in 3D you can, because you can make them have pipes that don't intersect. But anyway, in 2D you have to do one at a time. So we alternate them, but it's important. And then we're going to take this alternating shear flow and we're going to use it as the base fractal of a fractal vector field that we make. Okay, so we're going to have this shear flow repeated over many, 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 many scales, and it's the kind of multi-scale, and then we're going to do this homogenization analysis over and over again across infinitely many scales. And when we do that, it's not enough to say on large scales the effective, there's, in the homogenization community, we typically take infinite scale separation limits. Okay, and in this case we cannot, because we have to make a vector field with infinitely many scales, and so you can't just use all the scales on one limit. So we have to know that, when we're handling all these scales, that we homogenize one set of wiggles before we see the next set of wiggles so that they don't interact with each other and cause our proof to break. Okay? So we need to know on what scales these things homogenize, and that's up there. So the homogenization or the enhancement the homogenization or the enhancement of diffusivity for this problem is seen on length scales much, much larger than delta x, the same delta x that I wrote up there, and on time scales much, much larger than the delta t. Now, length scales and time scales are related through the diffusivity, and the diffusivity is exactly, that we computed is exactly the one that makes this and this kind of the same through that constitutive law, okay? All right, so I have 10 minutes. I want to discuss, let me see, so this is the point where I would...
You want to have some questions?
Yeah, I think that I was planning now to start to construct the fractal vector field, but maybe I let Vlad do that. Is that okay? And I stop now and I take your questions.